involving rotation. Today we will discuss about the time period of oscillating system involving rotation. Now first of all, consider here is a spring of spring constant K is attached at the center of the rod as shown in the figure. Let mass of the rod is m and length of the rod is L. The rod is pivoted here. For the calculation of time period of the rod, first of all, we have to provide an amplitude to the system. For this, we need to displace the rod by a small angle and then it should be released at this position. Because of the restoring torque about the hinge point of the rod, it oscillates about its mean position, and during the oscillation of the rod shows pure rotational motion about its center of rotation. Now for the calculation of time period, আমরা কতগুলো মেথড ফলো করতে পারি। ফার্স্ট আসবো মেথড নাম্বার 1। In method number 1, suppose here the rod is displaced. Let this angle is theta 0. Now in the equilibrium position, torque of the spring force and weight balance each other. Therefore, K into x0, let x0 be the extension, into L by 2, that equals to mg into L by 2. This is equation number 1. Here the torque of the spring force and torque of weight balance each other. Now, here equation of translational equilibrium cannot be written because of a hinge force acting at the point where rod is hinged. Its value and exact direction is unknown to us. Okay, that's why here the equation of translational equilibrium cannot be written. Now consider position of the rod. Here the position of the rod displaced by an angle of theta from this position. Here the rod is again displaced by a small amount theta. As shown in the figure, in this displaced position at any time t, the equation of motion of the particle for the rod is written like that. Net torque, that equals to I into alpha. So here K into x plus x0 into L by 2 minus mg into L by 2. This is the net torque at this displaced position, that equals to minus I into alpha. Now from equation number 1, we can write that kx into L by 2 equals to minus ml square by 3 into alpha, because moment of inertia of the rod is ml square by 3. So k into L by 2 into theta into L by 2, that equals to minus ml square by 3 into alpha. Therefore, alpha equals to minus 3 by 4 into k by m into theta. Here this L by 2 into theta, that is value of x. Here the negative sign shows that the restoring force is opposite to the displacement. Now compare this equation, this minus 3 by 4 into k by m into theta, with the standard equation of SHM, that equals to alpha is minus omega squared theta. So we can write that omega equals to 3 by 4 into k by m. If omega equals to 3 by 4 into k by m, then time period equals to 2 pi by omega. That means 2 pi into root over 4m by 3k. This is the time period of the oscillating system, and this is method number 1. Now next move to method number 2. That is the shortcut method, method number 2. For the application of this method, we have to find the equivalent mass and equivalent force constant as time period of the system, that equals to 2 pi into root over effective mass by effective spring constant. Now first of all, we have to calculate the effective spring constant. Number 1, when the axis of rotation is not the center of mass. When the axis of rotation is not the center of mass, here we have to calculate the effective spring constant, then we have to calculate the effective mass. First of all, আমরা effective spring constant calculate করব. When the axis of rotation is not the center of mass, then first of all, shift the end of the spring which is connected to any point of the rod to the center of mass of the body for finding n factor of the spring, where the n factor that equals to elongation of spring by displacement of the center of mass at that instant. Here n factor, this is the n factor of the spring. If the spring is connected to the center of mass, then there is no need to calculate n factor of the spring, and in this situation the k effective equals to k. Hence we can find that in this case the value of n that equals to 1. In this situation, spring is connected to the center of mass of the rod, so k effective equals to k and n equals to 1. Now next case, when the axis of rotation is the center of mass. If there are more than one spring is connected to the rigid body, then we have to bring all the springs to a single point by relating the displacement of the springs. Then n factor that equals to elongation in spring which has not be shifted divided by elongation of the spring which has to be shifted. This is n factor. This is n factor of the spring. Now we have to find out the effective mass. Next, we need to find the equivalent translational mass of the rigid body, and the equivalent mass can be calculated by the following relation, that effective mass equals to I by r square. Effective mass equals to I by r square, where I is the moment of inertia of the rigid body about the center of rotation, and r is the distance of the center of mass from the point of rotation. This value of r is only applicable if the axis of rotation is not the center of mass. In this case, r equals to L by 2. Therefore, effective mass, that equals to ml square by 3 divided by L by 2, that is 4 by 3 into m. Therefore, for the previous diagram, time period equals to 2 pi into root over effective mass is 4m by 3 and effective spring constant is k. Therefore, time period equals to 4 root of 2 pi into root over 4m by 3 k. এবার এই ফর্মুলা রিলেটেড একটা স্পেশাল প্রবলেম আর একটা এক্সাম্পল এই ফর্মুলা রিলেটেড আমরা একটু স্টাডি করব. কনসিডার a rod, consider a rod of mass m and length L is hinged at one end with a massless spring of spring constant k. Here we have to find out the time period of oscillation of the rod. Now here we apply the shortcut method. By the shortcut method, first of all, we have to calculate the n factor, and that n factor equals to elongation of spring divided by displacement of center of mass at that instant. Suppose elongation of the spring is x dash and consider displacement is x. Here x dash equals to L into theta and displacement is L by 2 into theta, that equals to 2, and effective spring constant, that equals to n square into k, and that equals to 4k. Hence the spring can be replaced by a spring of spring constant 4k connected to position C, means like this diagram. Here is center of mass, here is a spring constant 4k. Therefore, in this case, r equals to L by 2. Therefore, effective mass, that equals to I by r square. That means ml square by 3 divided by L square by 4. That is 4m by 3. That means time period, that is 2 pi into root over effective mass by effective spring constant, that is root over 4m by 3 into 4k, that is 2 pi into root over m by 3k. This is time period of the rod. Now move to next problem. In the next problem, consider a rod, of mass m and length L is hinged at one end to massless identical spring of constant k are attached to a rod, one at the free end of the spring and one at the free end of the spring and another at the center of mass. Here we have to find out the time period of the oscillating rod or time period of oscillation of the rod. So we have to find out the n factor, that is elongation of the spring by displacement of center of mass at that instant. Let elongation of the spring is x dash and displacement of center of mass, that is x. So x dash is L into theta and this is L by 2 into theta, that equals to 2. Therefore effective spring constant, that is n square into k, that equals to 4. Hence, the spring can be replaced by a spring of spring constant 4k connected at position C. Again, in this case, we need to find out the equivalent spring constant because there are two springs. Hence, the equivalent spring constant, that equals to 4k plus k, because the springs are in parallel combination, that is 5k. So my next diagram is like that. Here is the rod and here is a spring connected to position C having spring constant 5k. So in this case also R equals to L by 2, therefore effective mass, that is I by R square. I is m L square by 3 and that is L square by 4, that means 4m by 3. Hence the time period t equals to 2 pi into root over effective mass, that is 4m by 3, by spring constant, that is 5k. Therefore 2 pi into root over 4m by 15k. This is time period of the oscillating system.